Sorry for that. Okay. Yeah. Thanks very much for the invite and to the organizers. So I mean, it's a little hard to believe it was 16 months ago whenever I was last at an in-person meeting, and it was with Derek in Morocco when he invited me along. So I was very excited to come to Poland. So it'll be nice if in future editions we can actually
next time.
Yeah, next time for sure. But for now, I mean, it's been even in this virtual setting, it's been very nice. So yeah, what I'm going to talk about is something which I have been sort of dipping in and out of in the last couple of years, as this notion of quantum Darwinism and how do we describe a classically objective state from an underlying quantum dynamics. So whenever I told my partner about let's say what I was working on, I mean, she's a biologist and she took great umbrage with this notion of Darwinism. She kept on saying, you know, you bloody physicists keep sort of co-opting terms that you have no purchase over. But I said, well, Zurich can get away with it. But I mean, I guess what the goals of this talk is kind of twofold. On the one hand, I want to introduce this notion of Darwinism, and then I leave you to decide whether or not you love it or hate it, or whether or not you think it's a good way to try and describe how classical objectivity emerges. But then maybe the other, I think, almost more important aspect is to introduce everyone, if you're not familiar with it, with this notion of collision models, which I think are a tool for modeling really arbitrary open system dynamics in a very simple and efficient way. It's something which I kind of fell in love with whenever I worked with Bassano over in Milan for a couple of years. So really, it'll sort of come in a couple of parts where I'll talk a little bit about maybe sort of about 10 minutes each on these three papers. So just let me get into the swing of it. So yeah, so we start from, we saw this picture, I think, already in a couple of talks during the week, which I think really it gets to the core of what we try and do in open quantum systems. So we're trying to understand where this boundary between classicality and quantum effects kind of exists. And as we keep on doing better experiments and doing things, you know, that boundary just seems so very fluid. But I think, yeah, the overarching framework of, I mean, what we do here in this notion of channels, maps, and all that is trying to understand how a system talks with its environment and how that affects its dynamics and how that affects what sort of steady states or classical states that end up coming out. So I think where this whole framework starts from would be what Zurich did whenever he established this the framework of decoherence theory, which really sort of tells us what sort of classical-like states our system is going to be driven to. Really, what decoherence theory does is it tells us, well, if I have a system interacting with some environment, then the nature of how that system talks to the environment, the nature of that interaction selects certain states of the system which are essentially immune to the environmental effects. So while superpositions of those states get destroyed, the states themselves are somehow robust to the effect. And this is something which is really selected by the nature of the interaction. And this is where what Zurich would have called line selection, and he defined these states as pointer states. So these are the sort of states that are in, let's say, are the kind of classical states that our system wants to be driven towards. And that's what decoherence theory tells us. But what it ignores, and this is where quantum Darwinism comes in, is it ignores the kind of loftier question in some sense, which is how do we as observers determine whether or not, let's say, determine the classical state of the system? How do we arrive at let's say, an objective description of a given system, considering it goes through this quantum dynamics? And this is where we come into Darwinism. So if you're interested in getting into the area, I mean, the main place to start from would be this very nice progress article in Nature Physics from Zurich from a couple of years ago, 12, 13 years ago now. But I think I flash up just that there's a portion of it. I'm not going to read through this, but I've put the slides, sent the PDF of the slides over to the guys, so you can read this section in at your own convenience. But it really, Zurich in this article kind of describes the main motivation of Darwinism very succinctly, and I think very, very naturally. So if you're interested, have a read there. But the basic idea is that it moves beyond what what decoherence theory does, where decoherence theory focused purely on the properties of the system. And what it realizes is that if we want to talk about objectivity, we have to have some more information. We have to elevate the role of the environment to something a little bit more active. And so what we mostly do when we talk about open systems is we sort of phenomenologically take into account the effect of the environment, but then we trace it out. And so we just ignore, we treat it as a completely inaccessible set of degrees of freedom. And I think the key point of Darwinism that Zurich says is that that's not really the case. And he gives when describing it, he gives this very nice, I think, intuitive enough kind of picture, which is, we think about, well, how do we actually learn about a system? So we don't generally directly interact with it ourselves. What generally happens is that we indirectly learn information about it through its interaction with some sort of environment. And the example he gives in this Nature Physics paper is how are you all seeing the screen at the moment? You're not really measuring the screen itself. You're collecting scattered light through your eyes, and it's the information that scattered light brings to you tells you what it is that you're seeing. And then the crucial point that let's say of where this notion of Darwinism comes in is that you don't need access to the entirety of the environment in order to learn about what you're seeing. You only have to capture a small subset of that scattered light in order to learn everything. And that's really the kind of the ethos of Darwinism. So like I say, you can read all the rest of that in the PDFs later on, but the core quantity of interest that Zurich works with is this notion of mutual information, which I realize now, my bad that I didn't actually write, at a mathematical physics symposium, I didn't write the expression for mutual information, but thankfully Ali did it for me in the last talk. But to give a kind of, let's say, sort of intuitive idea of what it is that, let's say, the main figure of merit, Zurich takes this information theoretic approach, and he says, well, what can we ever say about the system? And really, it's just about whatever information it shares with the environment. And in particular, because of this idea that we only ever should have to capture a small portion of the environment to learn all the relevant information. So the picture that we normally get is that we have some system of interest here, and it's going to interact with some environment, which itself is fragmented. So we've got a whole bunch of different pieces of the environment. Decoherence theory tells us that the nature of how these fragments interact with the system will select the states, the classical states of the system that it will go into. But in terms of an objective state, the information that these fragments share with that system, or the information that the system through this interaction is able to spread throughout these fragments, that is what gives rise to objectivity. And so the telltale signatures are whenever we see what we call this redundancy plateau. So we look at this red curve here. What this is essentially saying is all of the information about the system I have is here. This is the entropy of the system. And if the mutual information that my system shares with some portion of the environment is equal to that entropy, equal to all of the available information about the system, then I can, from that fragment of the environment, I can learn everything there is to know about the system. And then if I have access to a larger fragment and I still can learn no more information, then this is indicative of a well-defined notion of objectivity. And what's more here, imagine me as an observer have access to, say, B1, one fragment, and you as an observer have access to maybe B4, 5, and 6. What this curve, this behavior is telling us is that I will have access to the same amount of information as you do, and we have access to the same information. And then by this definition, we will agree on the state of the system. And so this is the kind of ethos of how the notion of objectivity within this framework is defined. So now I take a small sort of 10-minute digression, and we'll loop back into the main, let's say, scientific aspect that I want to talk about. But I take a wee digression now to just talk in more general, let's say, in more general terms about the model, or the types of models that we want to, like, let's say, explore this phenomenology in. And what I like I said, what I started getting interested in a couple of years ago when I moved to Milan was this framework of collision models. And really, I mean, if you haven't worked on collision models, they're absolutely just beautifully simple ways in order to capture sort of generic or some fairly general open dynamics. So I think starting points for anyone who's interested would be these three papers from the early 2000s from some, well, I think some members of the audience here, and likely many people know these papers very well. But the basic ingredients that they covered, particularly in this PRL, was a notion of how does thermalization occur in a let's say a sort of more microscopic description. And the basic ingredients of a collision model are incredibly simple. We have a system of interest, and then we take our environment and we imagine that it's essentially like a conveyor belt of identical components. So we have the system, and then if we imagine the simplest possible case that the system is going to collide with one of these components. And if we imagine that all of these environmental fragments, essentially all of this conveyor belt, that they are all in identical thermal states, and if that system interaction is like a partial swap, then a single interaction will change the state of the system a little bit, and then it will move on and interact with the next guy, and we throw away all of the previous ancillas that the system has interacted with. What that gives rise to is precisely the same master equation dynamics that we would get from the, let's say, I would say, standard GKSL equation. So what's very nice here is that you have a very basic model. You have just two body interactions and a trace operation. And this gives rise, this captures precisely the same dynamics that is well studied in the master equation approach. So you can already see that the fact that the system moves forward and we do this tracing operation kind of implicitly brings in this Markovian approximation. Now, why I like collision models so much is their great versatility. I mean, you see here that we have these basic ingredients and we get a well-defined and well-studied physical dynamics that we're all familiar with, but I can tweak things very easily here. And that is kind of what has happened over the last, like, I guess, 10 plus years now within this framework is, well, there's nothing stopping me from adding like an additional interaction here between the environmental constituents, or adding pre-existing correlations within the environmental constituents, or doing anything like that, or adding some additional evolution to the system along the ways and seeing what happens with the dynamics. One of the advantages is because you're just dealing with simple two-body interactions and trace operations, you're guaranteed to have a physical dynamics. There's no concerns there. And so I'm biased, so I point directly to I think one of what I think is one of the very nice and sort of simple demonstrations of the versatility of this was this paper from Morrow and Rury, where they showed, you add a little bit of interactions here, you can tune and get and capture a nice non-Markovian dynamics. So I mean, this is one of the early instances I think where you can capture sort of you can start from a very well-defined Markovian case, and then you can see the emergence of non-Markovianity. I think for completeness, I should also mention that maybe a little bit less appreciated is there's this paper from the 60s from Jasitha Rao, and she really, I think, derived it's remarkable how similar to the formulation that we use today that this paper was. I mean, really, this paper was decades ahead of its time. So if you're interested in collision models, definitely go back and also have a look at this and be amazed at how sort of visionary I think this paper was. But as I guess a slight shameless publicity that I won't dwell on, but like over the last couple of years, I've played about with collision models in various guises with many collaborators. So as I've said, I mean, they're very natural for tuning things and looking at introducing that's a means of seeing non-Markovian dynamics. So we're able to kind of have a very precise knob for introducing it. And then we can use different frameworks to define it. Because I guess one of the major issues with trying to understand a non-Markovian dynamics, for instance, is that you need access to environmental degrees of freedom. What's very nice in these couple of papers was that we were able to think about, well, a collision model allows you to sort of single out I guess in some way similar to those reaction coordinate approaches, where you can define a kind of relevant subset of environmental degrees of freedom, and then you can play about with trying to see, well, what properties of those states or of those environmental components are what gives rise to this non-Markovian dynamics. So this is what we did in these couple of papers. I won't dwell on the other ones. We just played about with it a lot. But what I hope is kind of already clear is that the fact that a collision model naturally fragments your environment up into different constituents kind of lends itself very naturally to the framework of Darwinism. It somehow is sort of pre-built in to explore this, let's say, this framework a little bit more concretely. And so this is what we'll kind of focus on going on. But just to finish a little bit on, let's say, selling you the reason why you should all consider going and playing about with these collision models is, I think there's these two nice papers, one of which I had the good fortune to be involved in, that just came out this year, where really, rather than where let's say a lot of my work has focused on collision models as a tool for studying, let's say, sort of, I guess, fundamental kind of properties like the emergence of non-Markovianity, or like we'll see this objectivity. But more generally, they're an extremely efficient tool for simulating essentially arbitrary dynamics. So there's this very nice paper from the guys where they looked at arbitrary multipartite non-Markovian dynamics, and they demonstrate how in some sense how easily you can model it using the tools of a collision model. What we did in this paper that I think was just accepted yesterday for PRB, so it should be published soon enough, is we kind of brought together the tools of, let's say, advanced numerical techniques for simulating, let's say, some arbitrary dynamics, together with the basic aspects of a collision model. This idea that the system will interact with some fragment or some well-defined notion of a subset of environmental degrees of freedom. There will be a bit of an evolution for some time, and then we'll reset, or the system refresh in some sense that set of environmental degrees of freedom and go ahead. Now, what was remarkable here is that we took an arbitrary many-body, in some reasonable complex many-body system, and then we had it interacting with some sort of, the example we used like fermionic chains, and the dynamics of this is very, very involved to simulate. But by simply doing this refreshing approach and coupling it with these advanced numerical techniques, numerically exact arbitrary non-Markovian dynamics could be very efficiently ran. So I mean, I think this was a really, really nice bit of work that I just wanted to mention. And then to round off this kind of whistle-stop tour of collision models, just to say that they appear in so many guises and they've become a very popular tool. I think this slide is probably now a couple of years out of date. I updated it with one or two, but it's by no means anywhere near even a partial snapshot of what's going on. There's many of you in the audience, I'm sure, that have worked in some, let's say, on some level on these different collision models. But just to say that the great versatility of places which you can apply them. So, I mean, I think one of the great advantages, the fact that you have access to some of these environmental degrees of freedom, it makes it a very nice and robust framework for studying things like the thermodynamics. And I've already said about the non-Markovianity. There's some nice aspects where you can also apply it to things like quantum heat engines or in different formulations of master equations. So if you're interested in, let's say, learning a little bit more about it, myself and Bassano had the fortune to be invited to write this very short perspective. So really, this is, excluding the references, like 5.5 pages. So you can read it over a coffee, and it hopefully will give you the basic introduction to it. But I will make a small advert for what I know is a forthcoming, what I guess will be the canonical resource for studying quantum collision models, which should appear, I guess, at some point in the next couple of weeks, from Francesco and friends. And really, they're going to give a full treatise, I think, on all of the aspects of collision models and the current state of the art. Okay, So now let's go back to the main point of the talk, which was to discuss this notion of quantum Darwinism, and we're going to use a small modification the basic framework of a collision model. So let me just remind you what the key quantity of interest, which is just going to simply be the mutual information that the system shares with fragments of the environment. So the picture that we started with is going to be we're going to assume that the system interacts with some fragmented environment, and the geometry that we're going to end up working in is essentially like a spin star. You'll see in a certain limit, it's exactly equivalent. The picture we end up using, although we start from a collision model, it's essentially a spin star that has been well studied. And we know already from decoherence that the nature of this system environment interaction, this is going to be what's going to dictate the decoherence of the system. And we're just interested in playing about with this framework, this picture, to see, well, what are the properties, or what, how does this microscopic description change the emergence of these signatures of classical objectivity. So we're going to take our system, where everything that I'm going to talk about here, we just assume everything is a qubit for simplicity, but I think the results hold reasonably arbitrarily, and that the environment is fragmented up into n qubits, and all of these guys, everything starts just from a plus state. So we're going to take everything to be essentially in coherent superposition. And so what we'll focus on, I guess, we've done a couple of works on this over the last couple of years. I'll just talk about these two because I think they kind of get to the main crux of things. Where I'll talk a little bit here where we really have this sort of spin star picture, and really, I don't think there'll be anything overly shocking to anyone that we see here, that the nature of this microscopic description for a given initial configuration of the system and environment dictates whether or not you see objectivity. But it was nice to give us a little bit more of a handle on the mechanisms underlying the emergence of, let's say, these classically objective states. And then what I'll focus on is the sort of a very simple extension where we just make the system a little bit more complex. We add a little, let's say we take the system from being a single qubit to an interacting pair of qubits. And again, the actual model we study is something which is already well looked at in the literature, but from this Darwinistic framework, or with the question of classical objectivity, some interesting points emerge. So we start. So the first sort of toy calculations that we did here was really just to see how that microscopic interaction term, how the microscopic descriptions of how the system talks to the environmental constituents, how that affects the behavior of this mutual information. So you remember, for objectivity, what we want is that if I, as an observer, have access to some fragment of the environment, I should be able to learn all of the relevant system information from a small fragment. And if I increase the size of the fragment I have, I shouldn't be able to get any more information about the system. So if we take the interaction, so in everything we do here, we're going to take that the interaction G is sort of fixed arbitrarily. Well, yeah, that's basically arbitrary and sort of small in terms of whatever the energy splitting of the system is. That's sort of beside the point anyway. We look at just what we allow to happen is that in the first instance, we take the system and we imagine we fix the environment to be something like 6, 7, or 8 qubits. And then the system just randomly picks one of them to interact with. It interacts, it collides with them for a short period of time, and then it moves on and picks another one randomly. But we enforce a certain amount of uniformity. So on average, the system will randomly interact with everyone roughly the same amount of times. Now, if you know the model, essentially, if we take this ZZ interaction, remember everyone's initialized in the plus state, that's essentially just a pure dephasing. In fact, the order of this randomization doesn't really make any difference. But the important part, when we look at the behavior of this mutual information shared, so how much information a fragment of the environment, a fraction of the environment shares with the system, we get this nice redundancy plateau. So if I have access to a single qubit, 2 qubits, 3 qubits, 4 qubits, so on, all the way up until the full size of the environment, I only ever learn the only information I have access to is exactly all of the entropy of the system. This, again, maybe not so surprising. If I change the nature of the interaction to be something like an exchange interaction, well, again, solving this in general is a little bit trickier, but numerically running it for the, let's say for the same setup where we have everyone initialized in plus and the system randomly interacts with everybody, but roughly about the same number of times, you lose this characteristic signature. So you get this kind of, what these curves are telling us is that for this nature of interaction, there is no notion of objectivity. The larger the fragment of the environment I have access to, the more information about the system that I can learn. Now, again, this is not overly surprising considering what we already know from decoherence theory, that somehow the preferred states of the system that are somehow invariant to the interactions, they are singled out by the nature of this interaction and the initial states that we take. So it's not surprising that the pure dephasing gives us precisely what we were looking for here. But this model or this setup allows us to look a little bit more carefully at the structure of the overall system environment state. So again, this is not something which this is not something particularly brand new. We already kind of knew whenever you take this model to basically be the spin star setup, you can have a look at how this is going to evolve. So we fix the ZZ sort of interaction, this dephasing like interaction between the system and all of the environment. And what this essentially is you picture it at the system now, instead of randomly interacting, because all of these interaction terms commute, so the order doesn't really matter, we can now just picture really a kind of traditional spin star, but with this collisional idea where the system is sort of pulsing. So it collides with everyone and then stops, and collides with everyone, then stops. Again, you can go to a continuous time limit if you want. It doesn't make too much difference. But we solve to find what the overall state of the system and environment is. What we end up getting is that there's whenever we see this objective plateau, this redundancy plateau in the mutual information, this corresponds to a very specific type of state of the system and environment. And it's got this branching structure, where the pointer states of the system, the two pointer states branch out into two different paths, and the environmental states, they pick up a very particular, let's say a particular property. They end up getting this kind of equal and opposite phase associated to them. So the states that are the up states of the S are associated with the plus phase here, while the down states are associated with this minus phase. The specific details there are not so important. The crucial point is that this is a big entangled state. So in order for this objectivity, this redundancy to emerge, we need to build up very, very strong quantum correlations between the system and the whole environment. And in fact, it's basically this big GHZ state that the system generates. And that's what we need in order to get this classically objective state. So what we did we then asked the question, since we have access to all of the, we can very easily solve the whole model. We asked, well, what happens if I as an observer and you as another observer only have access to a single environmental degree of freedom, say a single qubit? What's the conditions that we need in order to see objectivity? So if we take the Darwinistic framework, the argument is that the entropy of the system should be equal to the mutual information shared between the system and say the single qubit, the single fragment of the environment that I have access to should be equal to the entropy of the system. And if things are objective, if you have access to a separate qubit of the environment, you should also have access to the same amount of the same information. Now, because of the symmetry of everything here, it's very easy to imagine that any single qubit of the environment will have the same, will basically be in the same state. So we just have a very simple look at, well, what happens during the dynamics. So here, N, we've just rescaled things in order for this pulsing picture. So N is basically the number of pulses that the system has had with this spin, let's say a spin star, or this bath of spins. So N is essentially equal to G times T, and we're taking that to be sufficiently small. Now, it's a finite size system. We're going to have some natural periodicity going on. But the important part is that after a certain number of these pulses, the entropy of the system will saturate. We've rescaled everything, so that's just equal to 1. And then there's this region where you can see the entropy is roughly equal to the mutual information. They're strictly only equal at one point, but there's a bit of a region where I guess, the information available is equal to roughly the entropy of the system. And this kind of, for this small environment that we're looking at, coincides with, you know, a decoherence of the environment, and also you have this obvious decoherence occurring in the the system decoheres, and you also have a decoherence in the state of the environment. But what happens when we scale up the size of so we take an order of magnitude larger spin bath? And then here, I guess one of the things that we noticed was that because the system is pulsing with a much larger environment, it decoheres much quicker. So the system loses all of its non-classical properties extremely quickly. So we see the entropy of the system saturates quickly, the coherence term drops off extremely quickly, but the mutual information still grows kind of comparatively slowly. And in fact, the behavior of the coherence term of the environment itself also is invariant. These two curves are identical. So this is basically saying is that even that decoherence of the system alone is not enough for objectivity to emerge. You need the system to talk to the whole environment to a sufficient degree. You need to build up, you need enough time for the system to build up the strong correlations that it needs with the environment in order for the right sort of state to be generated. So this is something which is a bit complementary, I guess, to a paper from Sabrina's group, where they talk about how you can have decoherence without generating any entanglement necessarily, but in order for us to get a classically objective state, you really need that the strong quantum entanglement, strong quantum correlations of a very particular form are established. But there is a subtlety. I mean, what happens if instead of having access to this extreme case of a single environmental constituent, I have access to maybe to a little bit more? And then what happens now is that, well, there's some critical is probably the wrong word. There's some particular fragment size that if I have access to, that the redundancy plateau will emerge. What this then means is that an individual constituent, say a single qubit of the environment, has a high degree of coherence. It'll share some non-classical correlations with the system, but a sufficiently large chunk of them will be enough for me to learn all of the information about the system, and will have washed out these sort of non-classical effects. But there's a little subtlety there, which, so Zwolak and Zurich have this nice paper where they talk about this complementarity between a measure of quantum correlations, this notion of quantum discord, and the classically accessible information. But there are criticisms of quantum Darwinism that arise precisely because of, let's say, some of the subtleties that are occurring in these curvy little areas. Because what can happen, what we know about mutual information is that it captures the total correlations. So it doesn't just tell us what the classical, or it tells us what the sum of the classical and quantum correlations are. And so criticism of quantum Darwinism have said, well, what if that mutual information is actually very quantum in nature? And there are examples where that happens. And this is kind of where we come into this more recent work, which we're just finishing up at the moment.
Sorry, Steve, have 5 minutes, please.
Yeah. I'll just quickly run through this. And so what we look at here was that we have we extend the model so we have basically the exact same setting, but now we imagine that we have instead of a single quantum system, we have two. And so the two of them are talking to each other, and we keep things solvable by taking this as like an excitation or an energy preserving interaction. But otherwise, everything is exactly the same as in the previous model. And now, if anyone who's familiar with this, who have done the calculations before, will see you can again solve this whole thing pretty readily. You can write down what the overall state of the system and the environment is, and then I guess, in my last 5 minutes, just to highlight the key points, is that this dephasing-like interaction between the two system qubits, so they're again pulsing with or just interacting with everybody in the environment at once, but because they have this mutual interaction, there's a decoupling in the basis states, in the pointer states of the system. So in the 0, 0 and 1, 1 states of the composite system, we see this telltale Darwinistic signatures. We see this kind of equal and opposite phase being imprinted on the environmental degrees of freedom, while in the single excitation subspace, it's a decoherence-free subspace. This is something, again, which is very well known in the literature. And what this means is that inside that single excitation subspace, you can have a lot of sloshing around of, you can have coherences built up within the system. They're going to interact with each other in this area. And this has a very interesting knock-on effect whenever we start trying to ask the question, well, is classicality synonymous with the notion of objectivity or not? And so I will quickly run through, I think I'll just focus on one aspect here, which is the core, again, the core quantity of interest for Darwinism is this mutual information between the system and an environmental fragment. And if we look at the composite system here, so the 2 qubits and the information that they share with a fragment of our spin bath, after, you know, after a sufficient amount of interactions through this dephasing-like interaction, big strong correlations are built up between the 0, 0 and 1, 1 states. And this then gives rise to this perfect redundancy again. We get exactly that precisely the conditions needed for quantum Darwinism. But if we look at the state of the system itself, because of this decoherence-free subspace, there's a sizable, there's a lot of non-classicality in the state. We can quantify it. I'll not go into the specifics here, but we can calculate a quantity, this quantum discord, which tells us how non-classical those correlations are. And it's a very non-classical state. And so this seems to throw up a little bit of a question, which is, well, I mean, there's been these alternative approaches to trying to define Darwinism, or to define objectivity. One of which uses what's called spectrum broadcasting structures, which focuses on the geometry of the states themselves. I'll not go into any more of this, except to say that there was a recent paper from Lee and Olaya Castro that showed if you add an additional constraint on this mutual information and you say, well, actually, it must be completely classical. It has to be, there has to be a vanishing discord between the system of interest and the environmental fragment. That is equivalent to getting one of these spectrum broadcasting structures. And they kind of unified the whole thing. But there is a subtlety that anybody who has worked on quantum discord will be familiar with, which is that it's an asymmetric quantity. And so what the guys did in this paper, what they said is that we need that mutual information is purely classical in nature, so the discord has to vanish. And they talked about measurements on the system alone without discussing the environment. So they assumed this, let's say, quantum discord based on measurements performed on the system. But somehow the motivation or the ethos of Darwinism was that the observers have access only to the environmental degrees of freedom. So really what should be relevant is what type of information we have at the level of measurements from the environment side. And so this is what we calculated. And so now in the last 1 minute, I will just say that for this situation where we have 2 qubits interacting with each other in such a way that it gives rise to this decoherence-free subspace, again, it's maybe not so surprising in hindsight, but what happens is that if I calculate that the overall state of the system and environment is a quantum classical state, what this means is that if I perform measurements on the system part, where there is this strong non-classicality established, then that state shares quantum discord with any environmental fragment. And then by the definitions of strong Darwinism and spectrum broadcasting structures, that state is non-classical and is arguably not, and they say is not objective. But if I go in the other direction and they say, well, as an observer, I only have access to the environmental degrees of freedom. If I perform measurements on the environmental state, it's completely classical. So in fact, that mutual information curve that we showed where we get the plateau, as far as the environment is concerned, that information is completely classical in nature. And so from that perspective, it's a perfectly classical and fully objective state. And so I think what this highlights is that there's a subtlety whenever we have more complex systems in discussing objectivity versus classicality. So I just mentioned that I think our paper is coming soon, but there's a complementary paper from Zurich and the guys that covers, I think, similar questions. So I think with that, I'm pretty much just about on time. So I will just say that if you're interested, love or hate the idea of Darwinism, have a read at some of the papers. The first part that we discussed with the spin star picture was all in this PRA from a few years ago. This idea of the composite system case is going to appear soon. There's a love or hate the entropy as a journal. There's a special issue on Zurich's, for Zurich's 70th birthday that will cover quantum Darwinism. And then just to say that if you take nothing else away from this talk, it's that collision models in general are just great crack to work with. They're a really fun framework to explore all aspects, I think, of open dynamics. So with that, I thank you very much. And with perhaps mild trepidation, we'll say I can take some questions.
Thank you very much, Steve, for this nice talk. We have some 3 minutes for questions. And if there's any question, please. Yes, go on.
I have one, if possible.
Yes, please.
Can you see me?
Yep.
Yes,
Okay.
I can see you and can hear you.
I'm not completely sure whether the question makes any sense, but yes, came to me. You know, Steve, that there is always a little bit of uncertainty when, let's say, one cannot start a story ab initio, right, and uses master equations phenomenologically for composite systems, on whether a local versus a global approach is more or less accurate. Mm-hmm. So can you say something about that if I think of the problem in this quantum Darwinism framework, or is not suitable for providing any further information?
No, well, so I think, I don't know, maybe if I'm getting the question right, I mean, I think a priori, like what quantum Darwinism sort of posits at the start is that we make this clean partition between the system and the environment, and then we just assume a unitary dynamic. So it doesn't try to take it, or it doesn't really matter, doesn't care so much about what the sort of master or what the underlying dynamics of the system is going to be after that.
Yeah, but you can, let's say, a posteriori compare conclusions, right? I'm thinking, for instance, of the system you can, in fact, do exact simulations, yeah? So just having a dynamic system. So in that case, I wonder, let's say, how do they compare the curves of the mutual information, right? And how would the different plateaus, so the objectivity conclusions you get, let's say, exact and the two type of master equations?
I think this is a very good question that I think me and Mauro talked to each other a little bit about. I mean, I don't think anyone has done it, and because you're right. I mean, if I imagine the dynamics of a system, and I could get the same dynamics from a variety of different means, whether or not both descriptions give the same objective, let's say, call it the same objective dynamic, or give rise to the same objectivity. I don't know. I don't know if anyone has checked it, but I mean, I think that's a kind of crucial test for this whole framework is, well, if two dynamics gives the same, or if two overall unitary dynamics gives the same reduced dynamics, are they both equally objective or not? Exactly. And I don't know, but I think it's something which we can check, and I guess we should do.
Okay, thanks.
Okay, maybe Steve, you can answer this question in 30 seconds. Nicoletta asked, maybe I missed it, but what's here the definition of classical objectivity?
So it's I think Olaya Castro paper has a very nice defines it. They say that objectivity is whenever the system, as an observer, I have access to fragments of the environment, and by performing measurements on my fragment, I learn the same information and I conclude the same state of the system. So if I have access to 5 qubits and you have access to a different 5 qubits of the same environment, that we both agree on what the state of the system is. That's what they call classical objectivity.
Okay.